Hello guys, let's focus on rotational equilibrium of a rigid body. Okay, I start from a bicycle. Let's say this bicycle is moving at a constant velocity. Constant velocity means that there is no translational acceleration. And because of that, the net force acting on the system is zero. This type of equilibrium was already considered in dynamics. We learned it. Now let's focus on one of the wheels, let's say back wheel. This back wheel may be acted by a clockwise torque due to the pedaling and maybe the anti-clockwise torque of friction, and they cancel each other. Why they cancel each other? Because I know that omega must be constant. Constant omega means zero angular acceleration. Zero angular acceleration immediately will result in zero net torque acting on that. Why? Because net torque is supposed to be equal to I alpha. We learned it in previous videos. So I can say if the system is acted by zero net torque, it means that omega is constant and vice versa. This is called a rotational equilibrium. It is different from translational equilibrium. Look at this bicycle. Let's say sometimes it's moving with acceleration, sometimes deceleration. So net force acting on this bicycle is not zero. Because of that, it has acceleration. And also net torque acting on the system on each wheel is not zero, because sometimes omega is increasing and sometimes it's decreasing. Let's redefine and restate Newton's first law in rotational motion. Formally, Newton's first law for angular motion may be stated as an object moves at a constant angular velocity, which may be zero, maybe not, unless an external torque acts on it. Means that omega is constant if and only if the net torque acting on the system is zero. Look at this satellite. Let's consider the satellite on circular orbit. The circular orbit exhibits a constant angular velocity. We know because omega is constant, and because of that delta omega over delta t is, which is alpha, is zero. So net torque acting on this satellite is zero. Can I say this satellite is totally in equilibrium? No, it is not. Angular equilibrium, yes. It doesn't have any angular acceleration, so angular equilibrium is confirmed. But translational equilibrium, no. It is anyway accelerated. You remember the centripetal acceleration. On this orbit, the object must be acted by gravitational force to hold it and to supply the centripetal acceleration for that. So it doesn't have translational equilibrium. The direction of the velocity is always changing. When I say velocity is constant, it's not valid for this object. Velocity is not constant. Although the speed is constant, but velocity is not, because direction of the velocity is always and continuously changing. So translational equilibrium and rotational equilibrium are two different topics. They may happen together, but separately one of them may be violated. Look at this lever. I have two non-equal masses on the ends of this rod, and it's supported by something at the center, a pivot at the center, okay? Guess the fulcrum, the pivot position to make the equilibrium. I ask you this question: how can I provide the equilibrium? Because for the time being, I know that if we release this system, here I have a large mg, and here we have a small mg. Let's say this mass is a smaller. It's 2 kilogram, I suppose, and this is 10 kilogram, okay? The right side is acted by larger force. But as the pivot is at the center, distances are equal. If I take the center of rotation here, I can say the clockwise torque is stronger than the anti-clockwise one. So systematically, we expect a kind of angular acceleration for this system. It won't remain at rest and won't be in rotational equilibrium. What should I do to take it to a kind of rotational equilibrium. Yeah, your guess is correct. I should displace the pivot rightward to cancel that higher torque. What do I mean by that? You remember here we had large mg and same distance. Now it has a smaller distance, you see? So the clockwise rotation, the clockwise torque is creating now might be equal to the anti-clockwise torque created by the blue object. The blue object, although it has a smaller weight, but anyway, the distance is large. So mg times d might be equal to mg times d. If they cancel each other, I mean if the clockwise and anti-clockwise torques cancel each other, basically we expect a constant omega or zero omega, and let's say zero angular acceleration. So the system is in rotational equilibrium. So for having rotational equilibrium, basically clockwise and anti-clockwise torques must cancel each other. This is a rule. This is actually a kind of confirmation on net torque acting on the system to be zero. Now guys, a very important exam trick. When a system is in rotational equilibrium, every point even out of the system can potentially be taken as the center of rotation. What does it mean? Let's say the system is at rest, not rotating. So the net torque and net force acting on that is zero. It's supported by a couple of pivots, and a couple of masses like M1 and M2 are attached to that. Okay? Where is the center of rotation of the system? We don't know because it's not rotating. So potentially point M, point N, point alpha, point beta, everywhere could be center of rotation. So what's the benefit of knowing that? I will tell you. You remember torque was force times the distance of the force to the center of rotation. Okay? If the distance to the center of rotation is zero, although there is a force, but there is no torque, and torque is eliminated. Let's say the question is given M1 as 2 kilogram, M2 as 1 kilogram, and they are looking for the reaction force of pivot Q. Here, FQ. I'm looking for FQ. How to find it? And I know all distances. Okay. I'm looking for FQ. I don't want to know anything about FP. What should I do? Let's say the point M is the center of rotation. Potentially every point could be that. So I take M. What's the benefit of that? Here there is a force Fp, of course, the reaction force of this pivot, and it doesn't have any torque. Regarding the center of rotation to be M, Fp is not actively participating in any torque, so it's eliminated. Basically, Fq is making an anti-clockwise torque. M2g and M1g, they are creating clockwise torque, and totally I have just 3 torques, 2 of them clockwise, 1 of them anti-clockwise. If I put them equal, they cancel each other, and I will find Fq. But what happened to Fp? Nothing. Fp doesn't have any active participation because Fp is exactly acting on the center of rotation. So it's not actively participating in any equilibrium, in rotational equilibrium equations. It's very important. So it's a very important exam trick. We will use it. Look at this question, for example. 2 objects of masses 1.5 kilogram and M are attached to the ends of a weightless horizontal rod, as shown in the diagram. There is a mass M, I don't know how much is it, and the other mass 1.5 kilogram, and the distances to the pivot are given 80 centimeter, 100 centimeter, okay? The rod is supported at point P, as we see, remains in equilibrium. Okay, so net torque and net force acting on that is 0. Equilibrium means full equilibrium. We are looking for first mass M. How to find the mass M? Guys, look at this. What are the forces acting on this system? A downward force of this, if the G is 10, it's supposed to be 15 Newton, mg. This is mg, I don't know how much is it, and it's also a reaction force of this pivot Fp. 3 forces, okay? They must cancel each other because the system is in equilibrium. So I can write Fp upward is equal to mg plus 15. I don't know Fp, I don't know mg, so this single equation cannot lead to any answer. I cannot use that for finding the mass m. What should I do? Let's use rotational equilibrium. Let's take the point P, exactly this point, the center of rotation. What's the benefit of that? If I do that, actively, I don't have any Fp in my rotational equations because Fp is eliminated. It doesn't have any torque, active torque, considering the P as the center of rotation. And the benefit is that this is a 15 Newton force creating an anti-clockwise torque, and this is mg creating a clockwise torque. If I put them equal, I will find mg. Done. So let's say the net torque clockwise is 0, so torque clockwise is equal to the torque anti-clockwise, and then we will continue like that. 1.5 g, it's 15 Newton times the distance is equal to mg times distance, the clockwise torque. Why the distances are written in non-SI units? Not important, because the units are cancelled. If you convert it to 0.8 meter and maybe 1 meter, again the answer will be the same. No need. Let's drop the g and then immediately find the mass to be 1.2 kilogram. So by taking the P as the center of rotation, I eliminated activation of Fp. So I can easily find the mg. Part B, the reaction force on the rod P. Now we can find it. It's very easy because I know the mg. Mg basically is 12 Newton and I know the 15. Total downward force is 12 plus 15 and upward force is just n, the normal force acted on the rod due to the pivot. Normal force must be equal to 12 plus 15, so it's 27. Done, we found the n. Okay? Another question. A uniform rod rests horizontally on two supports P and Q. It didn't mention if it has mass or it does not, okay? A mass 2 kilogram, this is the mass 2 kilogram, is attached to the rod. So we attach a mass. It comes to play after the system comes to rest and then it's added, okay? At a distance of 10 centimeter from P and 40 centimeter from Q, okay, we see that. What's the increase in the reaction force on the rod from each support after the mass has been attached to the rod? Guys, you know, at the beginning, we may have Fp here and we may have Fq here due to the mass of the rod. Okay. Now, when I attach this secondary mass, Fp will increase. Fq also will increase. They are asking how much they may increase. And G is 10. Okay. So basically, the increase in the weight of the system is 20 Newton. It is mg. Mg is 2 times 10. G is 10. 20 Newton. And this 20 Newton increase in the weight of the system will increase Fp and will increase Fq. Okay, let's forget about the initial value of Fp and Fq. And let's say Fp and Fq here are the increases in force due to this additional weight. Okay, so I can consider Fp the increase and Fq the increase and the reaction of each pivot after I add the 20 Newton weight. What should I do next? Okay, here you may consider the total net force acting on the system 0 and also total net torque acting on that, because The system is in both translational and rotational equilibrium. We will use all of them. First of all, let's take the mass here, the center of rotation. If I take it that, the 20 Newton is immediately eliminated because it doesn't have any activity in the total torque acting on the system. So basically I have a clockwise torque due to the FP and anti-clockwise torque due to the FQ. Okay, they cancel each other. So the torque will be FP times the distance and FQ times its distance. And the 20 Newton doesn't have any active participation. Here, this is the center of rotation. You know, potentially I can take every point as the center of rotation. So FP times 10 is equal to FQ times 40. You don't have to convert them to SI units because they are balanced, and whatever you may use, but just the same system of units is enough. So here I can conclude that FP is equal to 4FQ due to the implication of total net torque acting on the system 0, rotational equilibrium. What about the net force? Of course, net force is 0 because the system is at rest. Total upward forces are FP and FQ, and downward force is 20 Newton. Okay, just remember that FP and FQ are not the forces acted on the rod due to the whole mass of the system. They are just the increase. So I can say this 20 Newton is cancelled by the increase of FP plus FQ. So let's put them equal. FP plus FQ is 20. I can solve this set of equations together and find the answer. Here I can write FP to be 4FQ, so 4FQ plus FQ is equal to 20. 5FQ is equal to 20, so FQ will be 4, and so the other will be 16 Newton. I found the increase in the reaction force of each pivot due to this excess weight added to the system. Another question. A ladder of mass 12 kilogram leans against a vertical frictionless wall. So the wall doesn't have any friction, but the horizontal floor, it must have, of course. The ladder is at rest and makes an angle of 60 degrees with the floor. You see that. Draw the free body diagram showing the forces acting on the ladder. Let's do it. Guys, let's say this is the center of mass of the system, okay? And I will draw all the forces acting on that. One of the ever-existing forces that always we draw is the downward force of gravity. Downward, its weight, okay? Another is the F1, the reaction of the floor that must cancel the weight because, you know, the ladder is vertically at rest. So F1 is equal to W. When I draw them to a scale, I should check the size of F1 to be equal to W. The other is the reaction of the wall. Wall doesn't have any friction, so there is no vertical force on the ladder due to the wall, but F2 is horizontal and it's holding the ladder. And of course, it's pushing the ladder to the right, so leftward force to cancel that is the friction due to the contact of the ladder with the floor, so it's Fs. Is Fs equal to F2? Yes, it is, because the system is at rest. Horizontal equilibrium will imply Fs to be equal to F2. This is the free body diagram. Part B. Determine the magnitude of the reaction force between the wall and the ladder. They are looking for F2. Okay, for the time being, I don't want to know anything about F1 and I don't want to know anything about Fs. I'm looking for F2. Just be noted that I know the W. Because G is 10, mass of the ladder was given to be 12 kilograms, so W is supposed to be 120 Newton mg. Okay, I know the W and I'm gonna have F2. But I don't want to include F1 and Fs in my equations. Let's use that very important exam trick. let's say this is the center of rotation. Potentially, if the system is not rotating, every point in the space could be the center of rotation. Why taking this point as the center of rotation? Because F1 and Fs will be eliminated in rotational equations. They don't have any torque because they are acting on that point. So there is no torque due to F1 or Fs. So let's forget about them. But here I can draw a clock. This is a clock, okay? F2 will have a clockwise rotation and W anti-clockwise rotation. So if I write total clockwise rotation or torque is equal to total anti-clockwise, the clockwise will include F2 and the anti-clockwise will include W. The torque also is force times the efficient distance. Efficient distance is the distance from the force to the point of the center of the rotation. Here I extend F2, and this is the distance to the center of rotation. Let's say this is D2 for the F2. And also for the W, I can extend the W, and this is the distance of the W to the center of rotation. How to find them? It's very easy. Let's say the ladder has a length of L, okay, and it's making an angle of 60 degrees with the horizontal, okay. I'm looking for this distance from F2 to the ground because this is exactly the active distance for F2 to make its rotational effect, okay. This is L, and this is supposed to be the opposite side of this triangle, and this is the hypotenuse. So L sine of 60 degrees will be exactly the distance for F2 to the center of rotation. The other for W, look at this, it's very easy. W is acting at the center of the mass, center of the ladder, of course. So here I have half of the length of the ladder from W to the center of rotation as the hypotenuse. This is 60 degrees, and this is supposed to be the distance from the W to the center of rotation. So this is the adjacent side. It's supposed to be L over 2 cosine of 60 degrees, okay? This distance, L over 2 cosine of 60 degrees. Done. We can easily find them. So total clockwise is equal to total anti-clockwise. Clockwise means the torque due to the F2, anti-clockwise, the torque due to the W. Let's again remind you, this is L sine of 60 degrees. L is the length of the ladder, and this is the opposite side in this triangle. And the other is supposed to be this, as I told you in this triangle. This is L over 2, and this side is L over 2 cosine of 60 degrees, the distance for W to the center of rotation to find its torque. So let's activate the torques. F2 times distance, W times distance, okay? What happened to F1 and Fs? I gave them some transparency. They are not important. They don't have any torque. So let's just cross the L from both sides. And also you can write sine of 60 degrees to be square root of 3 over 2. And cosine of 60 to be a half. And here I have 1 over 2 as I drop the L. That's all. You can finalize it for F2 equals 20 square root of 3 Newton. This is the reaction of the wall on the ladder. Part C, calculate the minimum value of the coefficient of static friction between the floor and the ladder so that the ladder does not slide away from the wall. Oh, this case is concentrated on Fs. I told you Fs leftward must cancel the 20 square root of 3, which is F2. I told you. Why? Because horizontally the system has no acceleration. So I confirm that Fs is equal to that, and of course F1 is equal to 120, you know? And as we are looking for the minimum value of the coefficient of static friction, I can consider the system at the threshold of motion. Threshold of motion means that Fs can be written as mu s, a static coefficient of static friction, times the normal force. Normal force is F1. Okay, vertical normal force is F1. So I am allowed to write Fs to be mu s times F1 just because I'm looking for minimum value of coefficient of static friction. So the object is in threshold of motion. Okay, so let's use it. I apply this equation and I know that the F1 is the normal force we use for finding the Fs. Here I have F1 to be 120. I told you because vertically they should cancel each other. So it's 120. And left side I have Fs that is supposed to be equal to 20 square root of 3, as we found it already. So I will find mu s to be square root of 3 divided by 6. This is the minimum coefficient of static friction between the floor and the ladder. Leaning against wind, the other problem. Just Michael Jackson did it. I don't know if you have done it. Of course, Michael Jackson did it with some tricks, not leaning on the against the wind, but this guy can do it. There is a strong wind flowing rightward, let's say, and it's holding this guy. Draw a diagram showing the forces acting on the person. And also, you may have an assumption. Assume that the effect of wind can be represented by a single force acting horizontally through the person's center of mass. Okay, that's not very difficult. Let's say this is the center of mass of this guy. This is the wind force to the right and W downward. Guys, this W must be cancelled by a force, and also the wind force must be cancelled by a force. Why? Because this guy is at rest. So here we will have the Fs, the static friction, at the point when the feet are in touch with the ground, which cancels the Fw. You must draw them to a scale to show that Fs is equal to Fw, because this is a free body diagram. And also the vertical force of the normal force, the reaction of the ground, holding the person on the ground. They must be also equal and opposite. This is the free body diagram. Part B, the person remains in translational equilibrium. Means that F net acting on the system is 0. State the relationship between the magnitudes of the horizontal and the vertical forces acting on him. I told you Fw must be equal to Fs. This means that F net in horizontal direction x is 0. And the other is W equals n. Means F net in vertical direction is 0. Part C, to remain in rotational equilibrium, the person must lean at an angle of 65 degrees to the horizontal. His mass is 42 kg. Determine the magnitude of the force of air resistance acting on the person, the wind force. I'm looking for Fw. Okay, I know the W, but I don't want to include the normal force here and also the Fs. So let's say this is the center of rotation. It's the best strategy. If I take this point as the center of rotation, the normal force and also the Fs won't have any active participation in rotational equations. They don't have any torque. So let's take this point, okay? This is the point of action of Fw and the weight. This is this dashed line, the oblique dashed line. Center of rotation, and here is the point of action of these two forces. You know the torque is force times distance, but they must be perpendicular to each other. Wind force is horizontal, but to find its component perpendicular to D, I should make a small calculation. And also the W is downward. The component of W perpendicular to this D is supposed to be this. So I should continue for a small more calculations. Look at this. You can easily persuade yourself that this is 65 degrees. Why? Because this is horizontal, and this is the oblique dashed line. Okay? If this is 65, this is also 65. So the component of Fw perpendicular to the D is supposed to be FW sine of 65. This is 65 and this is the hypotenuse, so it's the opposite side. On the other hand, in this triangle, look at this. Here I have a 65 degrees, so here there is a 25 degrees because they add up to 90. Okay, 25. And if I draw a line like that, here is also 25. This is 25, this is also 25. And in this triangle, I can say this is W, this is 25 degrees, and so as the W is the hypotenuse, the opposite side is supposed to be W sine of 25. Okay, now let's put them equal, I mean the torques. Clockwise torque and counterclockwise torques must be equal. The clockwise is supposed to be the torque due to the wind force, and the anti-clockwise is the torque due to the W. Okay, so the wind force times 65 times D is equal to the weight force component times D. Why I don't have D anymore? I don't have to actually include the D because they have the same distance to the center of rotation. So forget about it. I can ignore it immediately. Just W is 42 times G, it's mg, and of course sine of 25 and sine of 65 can be found out of a calculator, and you will find it 190 Newton. This is the wind force acting on this guy. So you see that taking the center of rotation plays a very important and crucial role in solving the problem. I can exclude the unwanted forces acting on that point by taking the best selection. Of course, if you need to find another force like the normal force or whatever, you should take the center of rotation for another point. If you select that point, you will lose the n. That's exactly the exam trick. You always can use it. Thank you very much. Thank you for watching this video and being with me. Please go over the questions one by one again and make sure that you have learned everything in detail. See you soon.